Well, we're going to start with like a bit of a pop quiz, and this is taken from a paper published back in 1997 by Myers and Ashley in Chest, but it's very, very useful for us to kind of set up where we're going, and you'll need to do a little bit of thinking about this one. So I've blanked out some of the key words. So the point at which blank begins to accumulate in the blood, causing an increase in blank, is important to document clinically. Irrespective of the underlying mechanism or specific model that describes the process, the physiological changes associated with lactate accumulation have significant import for cardiopulmonary performance. These include metabolic blank, impaired muscle blank, hyperventilation, and altered oxygen blank, all of which contribute to impaired capacity blank. So have a little think about what those could be. Maybe just pause this recording to kind of think what about they're going to be, because I'm going to reveal what they are. And so what we end up with is this. The point at which lactate begins to accumulate in the blood, causing an increase in ventilation, is important to document. And we haven't discovered why that is the case. Why does lactate accumulating drive up ventilation? And that is very much what this session is about. Irrespective of the underlying mechanism or specific model that describes the process, the physiologic changes associated with lactate accumulation have significant import for cardiopulmonary performance. These include metabolic acidosis, impaired muscle contraction, hyperventilation, and altered oxygen kinetics, all of which contribute to impaired capacity to perform work. And they go on to write this. Again, I've blanked two of these out. In athletes, the level of work that can be sustained before blank, visually determined, is an accurate predictor of endurance blank. What could these be? These are a bit easier perhaps. In athletes, the level of work that can be sustained before lactate accumulation, visually determined, is an accurate predictor of endurance performance. And presumably these concepts have implications related to vocation, disability among patients with cardiovascular and pulmonary disease. So let's move that forward, and we're going to take this quite up to date. So this is a paper published in 2021 by Dave Paul and Harry Rossiter, working with George Brooks. And again, names that you should be absolutely accustomed with. And this very much sets up the notion of the gas exchange threshold and why it is so important to us. So this is from a paper published in the Journal of Physiology. And they write, the gas exchange threshold is defined as the metabolic rate at which excess CO2, i.e. in addition to the metabolic CO2 output, associated with a given VO2 is evolved proportional to the rate at which muscle and blood bicarbonate decrease, consequent to a buffering of metabolic acidosis, and which derives from a non-hyperventilatory mechanism. Or, put in another way, GET is identified by an increase in the VCO2-VO2 relationship with the V-slope plot, with evidence of absence of a frank hyperventilation. Gosh, there's a lot going on to unpack there, but the first thing is, it relates to what we saw in the previous section where we were doing a little bit of revision, which is the stuff from Myers and Ashley, which is, remember that they referred to this notion of a connection between lactate and ventilation. And actually what Dave Paul and colleagues are doing is they're kind of adding a little bit more of the underlying physiology here, which is this point, the gas exchange threshold, remember, which is our indication of the transition from moderate to heavy intensity exercise. That is the transition from predominantly aerobic to the onset of predominantly anaerobic metabolism. That point where lactate starts to accumulate is connected to excess CO2, but it appears, when we read between the lines, that there is a second source of CO2. You get CO2 which is released from the process of metabolism. So when you think about the idea of aerobic metabolism taking place in a mitochondria, you've got the tricarboxylic acid cycle, and what you start to get is the glucose molecule goes through glycolysis. It goes through that transition phase where it goes into the notion of acetyl coenzyme A. Acetyl coenzyme A then transitions into the TCA cycle. The breakdown from acetyl coenzyme A transitions into the TCA cycle. The byproduct of the TCA cycle is primarily hydrogen ions, which are then transported down the electron transport chain to derive ATP, but the CO2. So that explains why CO2 is produced. You get a CO2 byproduct really from substrate level metabolism. But Paul and colleagues are saying here, as is very much kind of the work from Myers and Ashley in the previous slides, that there's a second source of CO2 that is not coming from metabolism. And they go, well, actually, it's here that there is the addition to the metabolic CO2 output associated with a given VO2 is evolved proportional to the rate at which muscle and blood bicarbonate decrease consequent to a buffering of metabolic acidosis. So there is a second source of CO2, and it's the second source of CO2 that is directly linked to the appearance of lactate. And so this is that direct connection, and this is where I was saying at the start of this session that you need to fundamentally have a clear appreciation for the kinetics of lactate in relation to exercise and the idea of appearance and disappearance. And given the fact that we understand that there is a proportional relationship between exercise intensity and VO2, and what I mean by that is fundamentally for every increase in exercise intensity there's a proportional increase in VO2. But we also understand that there is a concurrent increase in CO2 in relation to exercise intensity to a given point. So as we get an increase in the ATP turnover rate, we get a concurrent increase in VO2. We also then get a concurrent increase in CO2 in relation to that because it's the byproduct of metabolism. What the paper here is alluding to is that actually that we may get a point where there's an increase in the VCO2-VO2 relationship. In other words, we get an increase in VCO2 which is disproportionate to the increase in VO2. In other words, VO2 goes up linearly to exercise intensity, and to all intents and purposes, so does CO2. But there becomes a point which is being suggested, which is the gas exchange threshold, which is the transition from aerobic to anaerobic metabolism, where CO2 loses that linear response in relation to exercise intensity, and we get this what's called the V-slope outcome. So let's have a think about this in terms of data and then try and connect this up physiologically. So if we look at this kind of data set that we've got here, it's really quite useful for us. What we can see here is we've got a number of data points. Here we've got kind of a blood lactate response to incremental exercise. And this is the point that we've been kind of referring to, which is the lactate turn point. It doesn't matter whether you're looking at panel A or panel B. So this is kind of our lactate turn point. Now, what you've then got sitting below here are a number of key parameters that we're going to look at in more detail in a moment. A couple that I want to look at here, particularly one I want to look at here is F, which is they're using this as breathing frequency. And I just want you to note that breathing frequency follows a fairly non-standard increase in relation to exercise intensity, and then you suddenly get this kick in breathing frequency at this point here, and it seems to tally with the lactate turn point, the second transition, the blood lactate response, indicating that there is absolutely a connection between the appearance of lactate in the circulation and, as Myers and Ashley were referring to, the ventilatory response. So now let's try and connect all of these together.